Welcome back. In this video, you will learn how to do integration by parts by using the tabular method. Let's get to it. Alright, so when we solve integrals using integration by parts the traditional way, we're going to encounter integrals that require using integration by parts multiple times in order to find the solution. And so this can become very tedious and also pretty time consuming, not to mention that there's plenty of opportunities for you to make a mistake along the way. And so in these situations, it's going to be helpful to know an alternative way to perform integration by parts that is quicker and simpler. And so that method is the tabular method that we're going to look at in this video. And so if you take a look at this integral here, we have the integral of x cubed times e to the power of x dx, and this is an integral that requires the use of integration by parts in order to solve it. In fact, it's going to require that we use integration by parts a total of 3 times in order to completely solve it. Right, this formula right here is what we used previously for integration by parts. And so we would use this formula a total of 3 times to solve the integral. But rather than doing that, what we're going to do instead is what is known as the tabular method. And so for the tabular method, we draw this table here, hence the word tabular, where one column is labeled with D and the other column is labeled with I. Now the first column D, which stands for derivative, is going to work with what you would typically set equal to U in the integration by parts process. And then our other column I, which stands for integral, is where we're going to work with the part of our integral that we would typically set equal to dv through the traditional way when using the formula for integration by parts. And so for this integral, we would want to set x cubed equal to u and e to the power of x dx equal to dv. And so I'll write x cubed in our derivative column and then e to the power of x in our integral column. And so what we're going to do is we're going to take turns taking the derivative of whatever is in a derivative column and integrating whatever is in the integral column. And we're going to keep on doing that until we reach a certain stopping point. And so I'll point that out when we get there, but let's just start by taking the derivative of x cubed and integrating e to the power of x. And so in this case, if we use the power rule for derivatives on x cubed, the derivative will be 3x squared, right? We multiply the exponent down and then subtract 1 from that exponent. And then the integral of e to the power of x is just itself, right? The integral will be e to the power of x. All right, and so let's do that again. Let's take the derivative of our new term. So the derivative of 3x squared will be 6x, right? 2 times 3 is 6. Subtract 1 from the exponent, and we have x to the first power. And then once again, the integral of e to the power of x is just e to the power of x. And then we'll do it again. The derivative of 6x is just 6, because the derivative of x to the first power is just equal to its coefficient. And then the integral of e to the power of x, once again, is just e to the power of x. Now we'll do this one more time. We're going to take the derivative of 6, which is just a constant, so the derivative will be 0. And then, of course, the integral of e to the power of x is still e to the power of x. Now we're going to stop there because we hit 0 in our derivative column. If you reach a value of 0 in either one of your columns, that is going to indicate that you can stop taking the derivative and stop integrating after that row of your table. All right, but we're not done setting up our table yet. There's one more thing we need to do, and that is put some signs in front of the derivative column. And so this part's pretty simple. You're going to start with a plus sign, and then you're going to alternate between plus and minus until you get to the bottom of your table. And so I'll write a minus in front of 3x squared, then we'll have plus 6x minus 6, and then plus 0. All right, and so now our table is completely set up. We can now use its contents to find the solution to this integral. And so here's what we're going to do. We're going to start with the first term in our derivative column, and we're going to multiply that by the second term in the integral column. In other words, we are moving down in a diagonal, and we're going to multiply positive x cubed by e to the power of x. And that's going to be the first term of our solution. So this integral will be equal to x cubed times e to the power of x, and then we're going to add that to the next term in the derivative column times the next integral term. So once again, we are multiplying diagonally, but this time we have negative 3x squared times e to the power of x. So we will be subtracting 3x squared times e to the power of x. And then let's move on to our next term. We're going to have positive 6x times e to the power of x, right? So now we're multiplying those two terms. And so we will add 6x times e to the power of x. And then we'll do that one more time for negative 6 and e to the power of x. So we'll multiply those two terms, and we'll have minus 6 times e to the power of x, and then we're done. We don't need to multiply 0 by anything because 0 times anything is just going to be 0, and so negative 6 times e to the power of x is the last term that we will get from this table. We just need to remember to add plus c to the end of our solution. And so then what we have right here is the antiderivative, or the solution, to this integral. This is what you would find if you were to use the traditional formula for integration by parts on this integral 3 times. It might have seemed like we really didn't save any time, but that's because this was the first time that we went through this process. But as you get used to using this table and the tabular method in general, it's going to be much quicker than using integration by parts multiple times for an integral. All right, and so let's take a look at another example. Okay, so here's our second example. We have the integral of x squared times cosine of 2x dx, and this integral, once again, will require the use of integration by parts. And so instead of using the formula that we would traditionally use, let's use the tabular method. I'll start by drawing our table. One of these columns will be d for derivative, and the other column will be I for integral or integration. Okay, and so now we want to choose a part from our integral that's going to start the derivative column, and then we want to choose another part that will start the integral column. And remember that whatever we would normally set equal to u for integration by parts, that's going to start the derivative column, and whatever we would use for dv, that's going to start the integral column. And so in this case, we're going to choose between x squared and cosine of 2x. And in this case, I know that if we take the derivative of x squared, that's going to get simpler. And so that's going to be a good choice for u, or what we want to use to start the derivative column. And so let's do that in this case. We'll start with x squared for the derivative column, which means that we will be left with cosine of 2x for the integral column. So we'll have cosine of 2x. Okay, and so let's work on filling out our derivative column first and taking the derivative until we reach 0. And so in this case, the derivative of x squared is 2x if you multiply the exponent down and subtract 1 from that exponent. And then if we take the derivative of 2x again, that derivative will be 2, right? The derivative of x to the first power is just equal to its coefficient. And then if we take the derivative again, the derivative of 2 is just 0, since 2 is a constant. All right, and so we'll stop there. We stop once we hit 0. And then let's work on filling out the integral column. So we're going to take the integral of cosine of 2x. And typically, in order to integrate a composite function like this, where we have 2x inside of a trig function, we would use u substitution. But there's actually a little trick here that when you are integrating a trig function like cosine and your inside function is just a constant times x, not x squared or anything, but just x, what you can do is integrate your trig function like normal, and then keep that same inside function, and then just divide by that constant multiple that's being multiplied by x. And so in this case, the integral of cosine is sine, and so we will have sine of 2x, and then we will divide by that constant multiple of 2. Okay, and so we can do that again. Let's integrate sine of 2x divided by 2. The integral of sine is negative cosine, so we'll have negative cosine of 2x, and that's still divided by 2, but then we need to divide by 2 again, which means we have 2 times 2 in the denominator, and that's just equal to 4, so this is divided by 4, so I'll write that. And then we need to integrate one more time, and so the integral of cosine is sine, so we're going to have negative sine of 2x divided by 4, but then we're going to divide by 2 again, so we'll have 4 times 2 in the denominator, but that's just going to be equal to 8, so we'll have 8. Okay, and then we're almost done setting up our table here. We want to add our signs along the side of our derivative column, so we'll start with a plus sign, and then we'll draw a negative sign, and then we'll alternate, so we have plus and then minus for the last row. Okay, and so now let's multiply diagonally and add up our terms to find the solution to this integral. All right, so this will be equal to positive x squared times sine of 2x divided by 2. So we'll have x squared times sine of 2x divided by 2. And then our next term will be negative 2x times negative cosine of 2x divided by 4. This negative and this negative will cancel out. So we will have plus 2x times cosine of 2x divided by 4. And then for our last term, we will have positive 2 times negative sine of 2x divided by 8. And so that will be equal to negative 2 times sine of 2x divided by 8. Okay, and then don't forget your plus c. All right, now this would be our final answer, but we can actually simplify it a little bit. 2/4 will reduce to 1/2, and 2/8 will reduce to 1/4. And then I'll also try to write all of these terms on one line. And so we'll have that this is equal to x squared times sine of 2x divided by 2 plus x times cosine of 2x divided by 2 minus sine of 2x divided by 4 plus c. Okay, and so then what we're left with here, these 4 terms, is the solution to this integral using integration by parts via the tabular method. It gives you the same answer that you would get if you were to use integration by parts with the traditional formula. Let's look at a different example. All right, so here's our next example. This time we have the integral of e to the power of 3x times sine x times dx. All right, and so once again, this is an integral that requires the use of integration by parts in order to solve. And so let's draw our table here so we can use the tabular method to solve it. And so I'll do that, and I'll label each of our columns. So this will be the derivative column, and then we'll have the integral column. And in this case, since we have a product of an exponential function and a trig function, it's not going to matter which you set equal to u and which you set equal to dv, or in this case, which one you put in the derivative column and which one you put in the integral column. Either way, you will still get a correct answer. But I'm going to choose to put the exponential function in the derivative column and the trig function in the integral column. Okay, and so I'll have e to the power of 3x in the derivative column and sine of x in the integral column. All right, and so let's start filling out our table here. We'll start by taking the derivative of e to the power of 3x, which is going to require the chain rule. So the derivative of e to the power of 3x is e to the power of 3x times the derivative of that exponent. And in this case, the derivative of 3x is just 3, so we'll multiply by 3. And now if we do that again, the derivative of 3 times e to the power of 3x will be the same function, but multiplied by 3 again. So we will have 9 times e to the power of 3x. Now you've probably noticed by this point that this derivative column is never going to reach 0, right? In our previous 2 examples, this column always reached 0, which told us where to stop. But in this case, that's not going to happen. And it's also not going to happen for our integral column. If we take the integral of sine x, that's equal to negative cosine x. So we'll have negative cosine x. And then if we take the integral again, the integral of cosine is sine. So this is negative sine x. And we're going to keep going back and forth with cosine and sine all the way down this column forever. And so the question is, how do we know when to stop? Well, what you want to look for is in a row of your table, you want to see if you can find a matching term to what is in the integrand of your original integral. In this case, we have the integral of e to the power of 3x times sine of x. And so ignoring the first row here, we want to look for a product of the terms between our rows that together would match what's in our integral, or are a multiple of what is in the integral. And so if you go to our third row here, notice that we have 9 times e to the power of 3x and negative sine of x. If we multiply these two terms together and ignore the negative 9, we have e to the power of 3x and sine x, which matches what's in our integral. And so when you see that you have a matching term or a multiple of what's in your integral, you can stop making your table. That is going to be the last row that you work with. All right, and so now that we know that we can stop, let's add our signs to the side of the derivative column. So we're going to have plus, then minus, then plus, and then we're going to go through the process as normal. We're going to multiply diagonally for our terms. But then when we get to the last term in our derivative column, we're going to do something a little bit different. And we'll get there, but let's just start by writing the first two terms. We're going to have that this integral is equal to positive e to the power of 3x times negative cosine x. So we're going to have negative e to the power of 3x times cosine x. And that will be added to negative 3 times e to the power of 3x times negative sine x. Now those negatives will cancel out, and so we will have plus 3 times e to the power of 3x times sine x. And then for our last term, since we do not have 0 at the bottom of our derivative column, we're going to multiply the two bottom terms together and integrate them. So we're going to multiply this way and integrate both those terms. So we will have plus the integral of negative 9 times e to the power of 3x times sine x times dx, right? We are integrating these two terms multiplied together. All right, and so then that's going to allow for something very nice to happen. But before we can look at that, let's first simplify a little bit. Let's pull this negative 9 to the outside of the integral. So we'll have that this is equal to negative e to the power of 3x times cosine x plus 3 times e to the power of 3x times sine x minus 9 times the integral of e to the power of 3x times sine of x dx. Now you might be looking at this integral and you're thinking, well, this didn't get us anywhere. That's exactly what we started with, but that's exactly what we want. Now that we have an integral that looks like what we started with, remember that these series of terms are equal to that integral. And so if we rewrite that, the integral of e to the power of 3x times sine x dx is equal to these terms, we can combine like integrals. We can add 9 times the integral of e to the power of 3x times sine of x dx to both sides of the integral and have 10 of those integrals on this side of the equation, and then we can just solve for that integral. And so if we do that, if we add 9 of these integrals to both sides of the equation, we'll have 10 times the integral of e to the power of 3x times sine x dx is equal to these two terms. So we'll have negative e to the power of 3x times cosine of x plus 3 times e to the power of 3x times sine of x. And then if we divide both sides by 10, then we will have solved for this integral and we'll have the solution to it. And so the integral of e to the power of 3x times sine x dx, which is the original integral up here, is equal to negative e to the power of 3x times cosine x divided by 10 plus 3 times e to the power of 3x times sine x divided by 10, and then don't forget to add plus c because you need that with a solution to an indefinite integral. And so this answer right here is the solution to this integral using the tabular method for integration by parts. All right, so if you notice that you're not going to get 0 in either of your columns for your table, you want to be on the lookout for a matching term or a product of two terms that is a multiple of what is in the integrand of the integral that you are trying to solve. Let's look at one more example for this video. All right, so here's our last example. We have the integral of x to the 4th power times the natural log of x dx. Now this is another integral that requires integration by parts in order to solve. In fact, this one could actually be solved by only using integration by parts one time, but I wanted to show you how to solve an integral like this with the tabular method anyway. Because the tabular method can be used in any situation, but it's going to be most advantageous when you have an integral that you know is going to require using integration by parts multiple times. Okay, and so let's start setting up our table here. I will draw it out, and we're going to have the derivative column and the integral column. And in this case, if we're going to use integration by parts, we need to identify what we would normally set equal to u and dv, and that will help us determine what will start each of these columns. And in this case, since we have an algebraic part times a logarithmic part, you're going to want to set the logarithm equal to u, or make that the beginning of your derivative column. Okay, and so then that would mean that x to the 4th power would be what we would set equal to dv, or in this case, what we're going to use for the integral column. So let's write that out. We're going to have the natural log of x in the derivative column, and x to the fourth power in the integral column. And by the way, if you're struggling to figure out what to put in each column or what you would set equal to u and dv, I recommend that you watch my previous lesson on integration by parts where I explain that in detail. All right, but let's fill out our table. Let's take the derivative of the natural log of x and integrate x to the fourth power. So the derivative of the natural log of x is just 1 divided by x. And then if we use the power rule of integration on x to the fourth power, we will add 1 to the exponent and then divide by that new exponent. And so the integral will be x to the fifth power divided by 5. Now if we fill out another row, if we take the derivative of 1 divided by x, remember that 1 divided by x is the same as x to the negative first power. And so if we use the power rule for derivatives on that, the derivative will be negative x to the negative second power, which is the same as negative 1 divided by x squared. So the derivative is negative 1 divided by x squared. And then if we integrate in our other column, we'll use the power rule of integration again, and we'll add 1 to our exponent and then divide by that exponent. So we'll have x to the sixth power divided by 5 times 6, and that would be equal to 30. And so I'll just rewrite that. We will have 30 in the denominator. And so we could continue to fill in more rows of this table, but I'm going to stop there because if you notice, this is going to go on forever, right? We're never going to hit 0 in either column. If we keep integrating this term, the power of x is just going to get larger and larger, and our denominator is also going to become a bigger number. And then if we keep taking the derivative in this column, we're just going to get smaller and smaller expressions where the x in the denominator is going to get a higher and higher power. And so these are never going to reach 0, and they're also never going to represent a product that will match what's in our integral, like with the previous example, right? We would need the natural log of x to show up somewhere in either one of our columns, but that's not going to happen. And so this is the third scenario that you could encounter when using the tabular method for integration by parts. And so in this case, what you want to look for is a product of two terms in a row that will be equal to something that you do know how to integrate, right? So in this case, our first row here is just what we started with, which we don't know how to integrate with an easy rule, right? We're trying to use integration by parts to solve that integral. And so we're going to ignore that row and look at the second row. We have 1 divided by x and x to the fifth power divided by 5. If we multiply those together, that would be equal to x to the fifth power divided by x times 5. And this x would reduce with one of the x's in the numerator, and so that would be equal to x to the fourth divided by 5. And we know how to integrate x to the fourth power divided by 5. It's just like integrating x to the fourth, but with a constant multiple of 1/5. And so we're actually going to stop our table after that second row. We actually don't need these two terms that we filled in. And so I'm going to erase all that. We're not going to need that to find the solution to our integral. We just need these two rows. And so if we add our signs to the side of the derivative column, we'll have plus and minus. We can then multiply the first term in our derivative column by the second term in our integral column. So we'll multiply diagonally. And then we will add the product of our bottom two terms integrated. And so that will look like this. Our integral will be equal to the natural log of x times x to the fifth power divided by 5. So we'll have the natural log of x times x to the fifth power divided by 5. And then we will add the integral of x to the fifth power divided by 5 times negative 1 divided by x. So we'll have x to the fifth power divided by 5 times negative 1 divided by x times dx. Okay, and so if we simplify, this will be equal to x to the fifth power times the natural log of x divided by 5. I just reordered the multiplication here. That doesn't matter. I just like to write x to the fifth power before the natural log of x. Doesn't really matter. But then we'll add that to this integral, which if we pull out this negative 1 and this 1/5, we will have minus 1/5 times the integral of x to the fifth power divided by x times dx. And x to the fifth power divided by x will leave us with x to the fourth power. So I'm just going to rewrite that, and we'll have x to the fourth power. And then we have a pretty simple term that we know how to integrate. And so let's do that. This will be equal to x to the fifth power times the natural log of x divided by 5 minus 1/5 times x to the fifth power divided by 5 plus c, right? If we use the power rule of integration, we add 1 to that exponent and then divide by that new exponent. And so x to the fifth divided by 5 is the integral of x to the fourth power. And so now, if we simplify this, this is equal to x to the fifth power times the natural log of x divided by 5 minus x to the fifth power divided by 25 plus c. And that is the solution to this integral using integration by parts, or more specifically, the tabular method. All right, so in conclusion, when you're going to use the tabular method for integration by parts, and you're setting up your table, there's 3 different stops that tell you when to stop filling out your table. The first one is the easiest. When either of your columns reaches 0, that tells you to stop, and then you can write out your solution. The second stop is if you see matching terms, or in other words, if the product of a row is the multiple of the original integrand, or what is inside your integral. And the third stop is if the product of a row is easily integrated, as you saw with our last example. If you can multiply 2 terms in a row together to get a nice term that can be integrated without integration by parts, then you want to stop there. Just remember that for these last 2 stops, you also need to add the integral of the product of the bottom 2 terms of your table to your solution. You don't just stop after multiplying diagonally across your columns. Okay, the only case where you don't need to add that integral is in the first stop where one of your columns reaches 0. All right, and so with that is all I had on integration by parts via the tabular method. If you want to see some more example problems, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.